where his job is to make important scientific discoveries. He also serves as a professor by courtesy in the Stanford University Department of Environmental Earth System Science. He's a lead author for the upcoming IPCC AR5 report and was coordinating lead author of the Oceans chapter for the 2005 IPCC report on carbon capture and storage. He's also authored numerous other reports, and he was elected Fellow of the American Geophysical Union in 2010. So it gives me great pleasure to invite Ken to speak to you in our tutorial on Geoengineering 101.
I'm in my stocking feet right now because technology didn't work this morning the way I wanted it to work, and that I was driving up Sand Hill Road and there was a big traffic jam. I didn't have a chance to go to my office and change out of my motorcycle stuff. So. But just before we start, I mean, geoengineering is a topic that many people have opinions about. And so, just so it's not completely me showering my views upon you, maybe is somebody walking in here with any kind of strong opinions one way or the other that you'd like to voice? Yes?
Isn't it sort of the last-ditch effort when we realize we're sailing over the cliff?
Okay, that's okay. I mean, that's one perspective. So, like, sort of the parachute or emergency exit plan. Anybody else have any other comments? Yes.
Isn't driving a car an act of geoengineering?
Okay, so what? Okay, that's a good question. Let's come back.
Yeah, I mean, along the lines that we know what it's going to do.
Okay, in that you're doing something and knowingly changing climate by driving a car. Yeah, so that gets into this distinction between intentionality, doing something knowingly and doing something intentionally. So, I mean, let's do this a little bit more and then we'll come back to that. Yes?
I guess I'm a little further along than Robert is, in that I think the math already shows that we're going to have to do it. And the question now is, how long will it take people to realize that we have to do it, and then what's the best way to do it?
Okay, so we have isn't it an emergency plan? And often these two perspectives of, it's an emergency plan that's on the shelf that might be someday in the future for an emergency. And then other people are saying, well, look, we're already in an emergency, and so it's time to take it off the shelf. Any other opening comments there? Okay, so 3 people just made comments about geoengineering. And so what was that comment referring to? So what is geoengineering? Does anybody want to try to say what it is? This is one of the things with geoengineering that it's a word that different people use in different ways and use to refer to a different set of activities. And so some people might think just driving your car to work in the morning is geoengineering. Other people would think, no, it's only if you're spraying aerosols in the stratosphere. And so often people make blanket statements, I'm for it, against it, it's good, it's bad. And if you dig into it a little bit more, you find out that really they're referring to different things, and the disagreements were disagreements over what was in their head when they were mentioning this topic. I think this, I'm not really going to go there too much, although we can extend in discussion. I think this question of, so one of the ways that geoengineering is defined is the intentional large-scale manipulation of Earth's geophysical systems, and often with the intent of reversing effects of anthropogenic climate change or something like this. But different people, whether you have to include that thing of what's the intent, but I think if you were to say intentionally try to alter global climate, I think this example of driving the car is really interesting because in the way I think about it, if I step on that gas pedal with the intent, and my intention is to have CO2 come out the tailpipe and heat the Earth, and so I'm sort of pushing this lever in order to heat the Earth, then to me that would constitute geoengineering. And if it's a knowing byproduct of something we do every day, obviously from the physical system doesn't care what our intention is, and it has the same physical effect. But to me, this idea of intentionality, it's the difference between sort of manslaughter and homicide or something like this. It's more of a legal distinction and not something that the climate system cares about. So, okay, let's just dive in here. So let me just start off with my, my overarching framework that I use to conceptualize about the solving this problem. And as I see it, we have this desire for improved well-being. We're trying to improve our lot. And in doing so, one of the ways we try to improve our sense of well-being is by consuming goods and services. So we build ourselves shelter, we get consumer products. But doing all this leads to the consumption of energy, as well as other natural resources, but especially the consumption of energy is leading to increased CO2 emissions, as well as other greenhouse gases, which is leading to increased CO2 concentrations in the atmosphere, which is leading to climate change and ocean acidification, which then impacts back on humans and ecosystems. And of course, the fear is that then these impacts on human ecosystems will work in the opposite sign and decrease our well-being as well as the well-being of ecosystems. And so this ends up being sort of a pernicious circle. And there are many intervention points along this circle. And so, different people define conservation and efficiency in different ways. But for me, this idea of conservation is that we're going to actually reduce our consumption of goods and services. And there's many, in a consumer society, there's many analogs between consuming consumer products and addiction, where people are trying to fill emotional needs by increased consumption. And so, there's, maybe people could read books instead of flying across oceans. But anyway, there's ways to improve well-being without increasing consumption of goods and services. That's a tougher thing to argue for the poorest countries of the world, obviously. Then efficiency is producing those goods and services with fewer material inputs or fewer inputs of energy and physical goods. Then there's low carbon energy systems, wind, solar, nuclear, and so on, which or low carbon emission energy, say fossil fuels with carbon capture and storage, that tries to provide that energy without the CO2 emission. And so what I'm going to talk about today is really these next two phases. And so one idea is if we're emitting the CO2, but we don't want it to accumulate in the atmosphere, is there a way to intervene here to prevent the CO2 emissions from leading to accumulation of CO2 in the atmosphere? And the simplest example of that one is planting trees, which take up carbon dioxide from the atmosphere. And so that's a relatively uncontroversial form of carbon dioxide removal. Somewhat more controversial is this idea of trying to break the link between CO2 or other greenhouse gases in the atmosphere and the amount of climate change. And this is this idea of reflecting some sunlight to space to prevent the Earth from heating up so much. Now, there are other ideas which we can discuss, but I'm not going to go into in detail, of trying to cool things by mixing the oceans or doing other things. And then this link between amount of climate change and amount of damage or impacts on humans and ecosystems, that's what adaptation's about, that we're trying to reduce the damage from climate change. And so I think, to my personal perspective is that this, solving this problem is difficult enough that we shouldn't take any of these things off the table as things we might want to consider doing. I think the more difficult question comes when you're addressing, if you think that all of these things need to be in the portfolio, what's the rational allocation of resources to these different things? And that rational allocation question comes up in two ways. One is in the research and development question, and the other is in the deployment question. And I wrote an op-ed which is in a handout, in I think it was in 5 years ago now in the New York Times, where I said that, well, and from an R&D perspective, we should have 100 times more research on this low carbon energy side than on the solar geoengineering side, but that we should not, so that R&D in this area should be in the portfolio, but that it should, it should be a relatively minor component of the R&D portfolio. Okay, so whenever I get, a good chunk of my work has to do with ocean acidification. This is not a talk on ocean acidification. I was almost told not to talk about ocean acidification, but I can't resist. But partly is this, that every time I present something about reflecting sunlight, people say, oh, it's not going to solve the ocean acidification problem. And I know that. And so this is just to convince you that I know that, but also to show you that this is, but it's also to say that this is a serious problem. And that we did this study now, this one's getting a little long in the tooth too, so 2008. And this is, these magenta dots show where coral reefs live. And they're threatened by warming, but they're also threatened by the oceans becoming more acidic. And basically when CO2 gets emitted to the atmosphere, most of it eventually gets absorbed by the ocean. In the ocean, CO2 becomes carbonic acid. And in high enough concentrations, it can dissolve shells and skeletons of marine organisms. But even in lower concentrations, it makes them harder to build their shells. And so this is omega aragonite, which is, aragonite is the mineral that coral reefs use to make their skeletons. And this is a measure of the thermodynamic potential that's helping to drive this skeleton formation. And so I think something like 98% of the corals in the world are where this pre-industrially, this 280 ppm atmosphere lived, where this degree of supersaturation was like 3.5 and almost all of them above 3.25. If we just look at how it's gone, now this is more or less 2005 CO2 levels, that already something like a third of the corals are probably, or close to half, are sort of unsustainable in the sense that they're living in places surrounded by water chemistry that was unable to sustain corals through geologic time. And then if you get to 450 ppm, which is just a few decades from now, 550 ppm is probably on current trajectory sometime shortly after, say, 50 years from now. And then we get towards end century scenarios that basically there's no place left in the ocean with the kind of chemistry that has historically been shown to support coral reefs. That's not to say that it's not possible that a coral reef might survive, but the risk is certainly high. So that's just an aside. So the basic, how does the Earth's climate system work? And this is about as simple as you could possibly make it, that sunlight comes in, heats the Earth, and then the Earth radiates that energy back to space. But some of that energy is absorbed by carbon dioxide and gets re-radiated down to the surface. And so it's analogous to you can think of CO2 in a way that it's like putting another blanket on the bed, and that you're there and there's a heat source and you're making it more difficult for that heat to get out, and so you warm up. And so another way, so basically we're kind of putting more blankets on the planet by putting more carbon dioxide in the atmosphere. And so the idea of solar geoengineering is to basically reduce this heating term, so compensate by, for having more blankets by, throwing your wife out of the bed or something like that. So, okay. And so just right away, you can tell that these are not going to do the same things. That if carbon dioxide absorbs energy in the middle of the atmosphere, and if you warm up the middle of the atmosphere relative to the surface, you're making the middle of the atmosphere less dense, and you tend to stabilize the whole vertical structure of the atmosphere. Whereas sunlight heats from below, and the same way you put a pot on a stove and you put the fire below, that it tends to make convection and tends to destabilize the atmosphere. And so sunlight and CO2 have different physical effects on the atmosphere, and so there's no reason to think that these two things are going to perfectly compensate. So the two basic ideas that have been lumped into the category geoengineering is this idea of removing these blankets, removing the excess carbon dioxide from the atmosphere, or diminishing the amount of sunlight coming down to the Earth. So I'm going to focus this on this area, but I'm going to start off just running through a bunch of ideas for removing CO2. And okay, this is not the latest version of this figure, but it's close enough. So it's so anyway, this is just an illustration of a range of ideas, and I'll go through them, and just to show that this is a kind of motley collection of different approaches, all of which have in common that they remove carbon dioxide from the atmosphere. So one idea is to fertilize the oceans. I'm going to run through each of these a little bit more later, and we can discuss them if you want. One idea is to fertilize the oceans. The other is to put alkaline materials in the ocean, like you can think of sodium hydroxide or lye or any kind of something that sort of would neutralize acids and alkaline materials, and that would tend to draw CO2 into the atmosphere, but would be buffered by these alkaline materials. There's also this idea of weathering materials on, same idea, but weathering materials on land. It goes into the ocean, and maybe the CO2 would be taken up in the groundwaters where this weathering is going on. There's other ideas of having industrial facilities, and you take minerals and take the, say, calcium or magnesium from these minerals, and you take CO2 from the atmosphere and you generate calcium carbonate bricks, something like this. Then there's this idea that sort of Klaus Lackner and David Keith have been pursuing, where you just remove CO2 from the atmosphere through industrial chemical processing techniques, get a relatively pure stream of CO2, compress it, and either put it just for geologic storage, or potentially it could even be inserted into the deep ocean. And then there's the idea of biomass energy with carbon capture and storage, so that you generate biomass, you put it in a power plant, but you capture the CO2 and inject it underground, or again, potentially in the ocean. And then I guess the last thing would be just biomass storage, where you just forget about this arrow to the power plant, but you just grow some plants. And so I guess the one thing I would say an outset about all of these things is that they all would, to solve the climate problem, these things would all need to be done at the scale of our current energy system. Right now our energy system's putting out something like 10 billion tons of carbon each year. And I forget what that is in moles, but 10 to the 16th moles or something like this. I forget what it is. But anyway, that for every molecule you put into the atmosphere, you need to have something react with that molecule and take that molecule back out. And so, maybe the taking out equipment can be half as expensive as the equipment that puts CO2 into the atmosphere, but more or less, whatever you do on the CO2 removal side has to be at the same scale as the energy system. And so, and since you have to take the CO2 out one molecule, molecule for molecule, that it's not going to be fast. So for example, if you want to, let me just go on to the next two ones that actually have more. I'll just do this one. So okay, let's just go through each of these in turn. So one idea, and this one is probably the one that's gained the most currency, and which some people, again, this question of what is the definition of geoengineering, some people don't consider planting a tree geoengineering, but that it's intentionally interfering with natural processes in order to affect the climate system. And the main problem is that the rate of carbon uptake by natural ecosystems tends to be relatively low. And if we put it into sort of energetic terms, we might have sort of this kind of on the order of a watt, and you can sort of double or half that if you want, but sort of on the order of a watt per meter squared going into fixing carbon. And if we think that today the average person in the world is using energy at the rate of 2 kilowatts per person, it's 2,000 joules per second, and for the average American, it's more on the order of 10 kilowatts, or 10,000 joules per second. And so for the average, if we think an average ecosystem is taking up some sort of carbon that's at a sort of chemical, that's a rate of chemical fixation comparable on the order of a watt per meter squared, and we're using 10,000 watts per meter squared, 10,000 watts, that you would need a hectare or 100 meters by 100 meters area per person of growing forest to take all this out. And so it's the kind of thing that if it makes sense to do, if it gives you other benefits like biodiversity or protection of natural resources, or that there are a lot of co-benefits from preserving forests or reforesting. And one of those, and there are benefits often in terms of the carbon cycle and the climate system, but it's not a quantitative solution to the problem. It's a kind of thing that could potentially contribute.
And you mean there's just not enough land area to do it?
Yeah, basically. You're land limited. Okay, I have a slide on that, so we'll come up with that in a second. So one of the ways to get around the land area issue is this idea of biomass energy with carbon capture and storage. And one of the problems with growing a forest is you grow a forest and then you have to preserve it forever. And you sort of use that land once for storing carbon. But if you can harvest that carbon, burn it in a power plant, first of all, you're substituting for a fossil fuel, and so you're reducing the emissions side by burning the biomass. And then by doing carbon capture and storage, you get a double benefit, that you both displace, by using the biofuels, displace a fossil fuel, and then by using carbon capture and storage, you end up with a net carbon negative energy system. I'm not a power plant engineer. My understanding from power plant engineers is that when you get above 10% biomass co-firing, you start getting burning at lower temperatures, and there's issues of getting efficiencies. The other issues have to do with transportation costs, that if you have a 1 gigawatt power plant and you're only getting this sort of 1 watt per square meter out of your ecosystem, that 1 gigawatt power plant very quickly uses up all the biomass that's nearby, and then you have these transportation costs of trying to bring the biomass to power plants. And so, I think there are certain places where this definitely makes sense. One of the places where these biomass options make the most sense are places like sugar, where you already say have a sugar mill, and they're already collecting all the biomass and bringing it to make sugar, and then you have this big waste pile of crushed sugar cane. But again, those kind of opportunities are kind of nice marginal things, but they're not quantitative solutions to the overall problem. So then again, this is sort of maybe not the latest design ideas, but sort of Klaus Lackner and David Keith and others have been working on this idea of industrialized CO2 removal. And it's known that if you add an alkaline material, say lye, sodium hydroxide is the poster child, to water, it will absorb CO2 out of the atmosphere. It's a known chemical reaction. And in the paper industry, where they're bleaching papers and then recycling materials, there are processes to recapture the CO2 and recapture the alkaline materials. And it's been demonstrated in the lab that you can make an alkaline solution, have it absorb CO2 from the atmosphere. You can then process that solution to get the CO2 back out and recycle the alkaline materials. And it's really, and so this works from a, both an engineering and a thermodynamic sense. And the question is, is it economic? And so again, the basic story is, you're building something that's, kind of like an oil refinery or something, except it's going the other way. And it's going to be more or less the same scale as your energy system. And if you're going to be building these kind of giant industrial complexes, maybe you might want to just build carbon emission-free energy systems rather than having no, but there are other, depending on your pricing, different people estimate this at different amounts of money. So the optimists say it's, the optimists think they could compete with carbon capture and storage from power plants. The pessimists think it'll cost an order of magnitude faster, more. And the thing is this, that power plant flue gases are typically something like 10% CO2. The atmosphere is 0.04% CO2. And so it's the question is, well, why would you try to extract the CO2 from something that's 0.04% CO2 rather than a power plant flue gas that's 10% CO2? And most observers think, well, this is really an end game kind of thing, that you're really going to, it's after we've already captured CO2 from all the power plants. If we're really desperate to get more CO2 out of the system, this could be an approach. One of the challenges to decarbonizing the energy system are things like long-distance trucking, aviation fuels, and so on. And so this, at least from a theoretical perspective, gives you the idea that, well, maybe you still run the aviation industry on fossil fuels, but then you pay to withdraw the CO2 out later. And so, I mean, to me, it's either end game, or the other kind of place where this has application is you go to a user that doesn't care about how much something costs, like the US military. And if you're on a nuclear-powered aircraft carrier and you want to make jet fuels, and you can get hydrogen from water, which you can split electrolytically, and then you need a carbon source to react with that hydrogen to make jet fuels, that this could be a process that would let you get, but that's an energy-intensive thing. Yes?
So you have one thing you haven't talked about in these other alternatives so far is how much energy they eat. So if you're generating energy and then you're trying to get rid of the carbon from it, how much of the energy you generated did you use up just doing it?
Yeah, I forget. I mean, this works out positive. I forget what the exact numbers are, but I think it's, I think it's less than half, but probably more than a third or something like this, somewhere in this ballpark. But I forget the exact numbers, but it's a significant energetic hit. Okay, so I don't want to spend too much time going through all these, but this idea that if you weather silicate rocks and react them with CO2, you can make carbonate rocks and silica, which is sand. And there's a number of people like Kurt Zen's house from, I think MIT or Harvard, I forget which, proposed this approach. And the basic problem, again, is this, that if you were to compress, we're putting out around 10 gigatons of carbon, so over 30 gigatons of carbon dioxide each year. If you were to compress that to each gigaton of carbon dioxide, if compressed to the density of supercritical or density of water, say, would be 30 cubic kilometers of material. And so, that if you were to quantitatively do this much reaction, you'd need probably some tens of cubic kilometers of silicate material that you would need to mine and grind each year. And again, it's just a question of, is something at this scale, is putting a mining industry at this scale, which it's not 2 orders of magnitude bigger than the current mining industries, but it might be an order of magnitude bigger, something like this. And another sort of related idea is, instead of making carbonate bricks, take weather rocks and dissolve the material in the ocean, and it has the same mass. Basically, you still don't get around the mass problems, that our energy system is so huge that anything that you do that works chemically has to be done at the scale of the energy system, and so it's going to be that order of magnitude of effort. So one thing that's been suggested, somebody mentioned this idea of storing carbon in the oceans, is this idea. This is a satellite photo of a fertilized patch where people threw iron in the ocean. And there are parts of the ocean where there are nutrients like phosphorus and nitrogen sitting on the top of the ocean, but there's not much life going on or not much productivity because the life in the ocean, the productivity in the ocean is limited by the availability of micronutrients, especially iron. And so one idea has been to throw some iron on the ocean, and the ratio of iron to carbon in plankton is like 1 to 50,000. And so it's one of the places where you do get a multiplier. Everything else I've been showing you, you kind of need 1 to 1. And this one promises like a 1 to 50,000. And the idea is that you put in, 1 atom of iron that allows a plankton to grow. It takes in 50,000 atoms of carbon, and then ideally it sinks when it dies to the bottom of the ocean. And then some CO2 comes in the atmosphere, replacing that plankton. And your model results suggest that, if we did, huge swatches of the ocean, we might be able to get a gigaton of carbon a year this way, so sort of 10% of current emissions. So that if you were willing to convert most of the oceans, or at least say a third of the ocean area, Southern Ocean, there's only certain places where this works, where you're iron limited, which are the Southern Ocean, Equatorial Pacific, a few other places. So if you were to, say, transform 1/3 of the ocean and start doing this, you might be able to take up a gigaton and solve 10% of the problem. So again, it's kind of in the biomass category where it's something that could potentially marginally, be a marginal contributor. It's not a solution. There's another sort of, so I mean, the one thing I see with this is that this one could actually be economic. It's sort of, this is one where it might, people aren't certain how well this will really work, how long the carbon will be stored. It might end up being cheaper than, say, carbon capture and storage or nuclear power or something like that. And so then this one, the controversy is over. We've converted much of the land ecosystems from natural ecosystems to managed ecosystems. Do we want to do the same thing to the ocean in order to solve 10% of our current emissions problem? Yes?
Is this like will the phosphorus and nitrogen run out at some point, or will the phosphorus and nitrogen run out in those oceans at some point, or is it?
Yeah. Okay, you can do more. At first, you get more. So the question is, can you keep doing this, or is it sort of like you use up the phosphorus and so on once, and then you're done? So the way the ocean works is because all this organic matter has sunk to the bottom of the ocean, the deep ocean is rich in nutrients and carbon. And that water gets mixed up to the surface. And where there's nutrients and light, that's where plants and algae and so on can grow. And then when it dies, it sinks back down. And so you can get sort of a kick that might be sort of, I forget the exact number, but maybe like 5 times bigger than this kind of sustainable level of increased carbon flux out of the surface of the ocean just by adding the nitrogen, the iron at first. And because you're using that reservoir that's sitting in the surface of the ocean. But once you've used that, then you're kind of limited to the additional phosphorus and nitrogen that mixes up. And so really the first, if you were to fertilize the entire ocean today, that for the first year you might get 10 gigatons of carbon. But within a few years you would deplete the phosphorus and nitrogen. And so that 1 gigaton per year is kind of the century scale sustainable level in the most extreme kind of case. And there's another factor that needs to be considered also is that 1 gigaton per year takes also into account that this carbon that gets transported into the deep ocean doesn't stay there forever. And so it starts getting, as these nutrients get mixed up, the carbon also gets mixed up. And so at a certain point, you're kind of adding more iron just to kind of keep the carbon in there that you put in a half century ago. And so there's diminishing yields with time. But on the century scale, from an extreme modeling perspective, it might be a gigaton per year. I think people think from a more sort of practical level, if you were actually going to deploy something, that a couple of tenths of a gigaton per year might be a more realistic thing. And so then the question comes, do we want to sort of go down this road? Right now energy use, if you think GDP over this century is going to go up 3% a year, and you think that efficiency is going to improve 1% a year, then that says, well, emissions are going up more or less 2% a year if we don't change the fuel mix that much, which means a doubling of emissions every 35 years. And so if we're 10 gigatons carbon now, and it's 20 gigatons in 35 years, and 40 gigatons in 70 years, something like this, and then you're managing to get a couple of tenths of a gigaton doing this. Is that really the best way of sort of managing ocean resources and handling this problem? Yes?
A concern, I think, as a forecaster, I would have is thinking, what happens when permafrost starts to soften? And we start getting an enormous global warming potential, and that methane eventually becomes CO2. Don't you want to get in front of that heating curve? And so shouldn't our efforts today be to really avoid any more significant warming and softening of this? Because these are secondary feedbacks that would dwarf anything that we could do.
Okay, let me get to this, because this is actually where I'm getting to, and I think I'm spending too much time on this carbon dioxide removal business. There's this other idea of storing carbon in soils, which is, to me, there's sort of two end members. Is either you grow biomass and you store that biomass somewhere, or you burn it and you have that biomass substitute for fossil fuels. And biochar is somewhere in between, where you sort of halfway burn it and halfway bury the reduced carbon. Again, it's the kind of thing that it comes back to the whole area density, that all the biomass options depend on photosynthetic yields, and you just don't get that much. All the biomass-based things are very area intensive. So there's one thing this is a paper that we did, I guess, last year. And what we did is we just said, okay, what happens if we, so this is like a business as usual scenario. And then I think in 2050, we said, okay, let's zero emissions. So, and so if you cut off instantaneously all CO2 emissions, the CO2 in the atmosphere starts declining as it gets absorbed by the land biosphere and the oceans. Then we said, okay, what happens if you remove all the CO2 from the atmosphere once? And what happens is the CO2 comes down to pre-industrial levels, but then CO2 that had been previously absorbed by the biosphere or by the oceans starts coming back out and coming back up into the atmosphere. And so then, but what you can do is you can pull all the CO2 out, and then as this stuff comes out of the oceans and the biosphere, you keep sucking it out of the atmosphere. And so this is from CO2 concentrations. And so this is the temperature effects of that. And so there are thermal lags in the climate system. And so in the IPCC did one more scenario would have been good, is just to hold the CO2 levels constant there. And if you would have held the CO2 levels constant, the Earth would continue to warm, because there's kind of more warming in the pipeline, because the ocean hasn't heated up yet, and it's kind of keeping the Earth cooler than its equilibrium. And so if we would have kept CO2 emissions constant, temperatures would still continue increasing. And zeroing emissions, different models might give slightly different slopes, but to a first approximation, zero emissions does not cause temperature to decrease. So decreasing emissions itself does not cause the Earth to cool. That zeroing emissions is what you need to do just to prevent further warming. If you remove all the CO2 from the atmosphere, excess CO2 from the atmosphere, because the biosphere and the ocean degasses the stuff that it had formerly picked up back to the atmosphere, that it only removes around half the global warming. And to kind of get back to the pre-industrial temperatures, you also have to continue taking additional CO2 out of the atmosphere for a long time into the future as that stuff degasses from the ocean and biosphere. Now, it doesn't show up on this scale, but if you do cool substantially within decades. Of course, this is an extreme case where we've suddenly, instantaneously reduced emissions. But it's good. One thing to bear in mind is that a one-time complete removal of all the excess CO2 from the atmosphere only gets rid of half the warming. And that the other thing to bear in mind is that even if we could go to zero emissions tomorrow, that would just prevent further warming. It wouldn't even set us for cooling for many centuries. Okay, so if even going to zero emissions, so we had heard this concern about the permafrost, and my sense of the people who know the most about permafrost think that a sudden degassing of huge amounts of methane is unlikely, but I don't think it's certainly not what's that?
Sustained, not sudden. On a geological time.
Yeah, but anyway, there's some, there are times in the past, at least some people believe, say, in the Paleocene-Eocene thermal maximum 55 million years ago, that there may have been slumping of shelf sediments that had a sudden release of methane. And so, even if you think it's low probability, I think you can't rule these things out. But I think most people would think it's a low probability. And if even zeroing emissions only prevents further warming, if you've already got enough warming to send this methane out, or another concern is if the ice sheets, again, most glaciologists, I think, now think that the ice sheets will melt not so quickly that that we're unlikely to see I was at one meeting with a bunch of glaciologists, and they said for this century, under business as usual, their central estimate was something like 60 centimeters in this century of sea level rise. And they sort of best guess at uncertainties was maybe 30 centimeters to 1.2 meters. And again, it's one of these things you can't rule out a couple of meters sea level rise in a century. It's happened in the geologic past, but it's probably not likely. But if we did get into that situation where we were facing a couple of meters in a century, that doing something like even cutting emissions to zero would be too late and wouldn't be enough to do anything. Yeah, so anyway, I guess we don't need to go into this one, but just this, temperature record of the last century plus, and I'm always amazed at people who take this last little bit of it and use this record to suggest that there's no such thing as increasing global temperatures. Anyway, but there's some nice work by David Battisti and Ros Naylor, who's a professor here at David Battisti's University of Washington, Ros Naylor is here at Stanford, looking at climate model results, saying, well, what fraction of summers in mid-century are going to be hotter than the hottest on record? And, in many parts of the world, it's in this, over half the summers will be hotter than the hottest on record so far. But if you go to the end of the century, over huge chunks of the planet, and chunks of the planet where lots of people live and lots of poor people live, almost every summer is going to be hotter than the hottest summer on record. And, maybe, I'm not a crop biophysiologist, but, that there are, reaction rates go up with increasing temperature, and there's only a certain scope to develop crops that are heat resistant, and already in the tropics, many crops are heat stressed. And so while we might think that the slumping of methane is a high risk but low probability outcome, and maybe the rapid collapse of ice sheets is a low probability but high damage outcome, that I think the probability of having serious problems with crop productivity in the tropics is not a low probability outcome. And so now one of the things that has come up in crop modeling is that the growing seasons tend to get longer in the mid-latitudes, and so most of the models that predict crop decreases in the tropics, many of them predict increases in global crop productivity, but that it's basically the rich northern countries getting increased productivity with decreases in productivity in the tropics. And so, that so you could say, well, look, if there are famines, famines do develop through some of these red blotchy regions, that there's no intrinsic reason why anybody has to go hungry, because there will be enough food in the world if social systems are managed well. And so that if there are famines, it's not just the climate change, but it's also the failure of social systems to address these climate damages in some kind of way that makes societies more resilient. And so I used to think of geoengineering as a response to a climate crisis, whereas I've come to the thinking more that there's no such thing as just a climate crisis, that everything is there's a crisis that involves social institutional responses, and that also involves the physical climate system, and that if we were able to develop the right social systems, that, well, we might not be able to save coral reefs because there's nothing you can do realistically, I don't think, if we don't reduce emissions to save coral reefs, but there's no reason that people have to starve. And so that if people get desperate and feel like, oh, I have to do geoengineering, it's not, the climate driver might be the immediate proximal cause, but it's really also a failure of institutional response. And I think this was brought home to me really looking at that 2009 subprime mortgage crisis. Because if you look at what the Stern report projects for the range of climate damages from not doing anything about CO2 emissions, the low end of Stern's climate damage estimates 5% of global GDP. 5% of global GDP is what we lost in 2009 due to the subprime mortgage crisis. And so you had bad, and nothing physical changed, right? You had homeowners in the United States realizing that their mortgage was bigger than the value of their house. So they decided, well, I'll declare bankruptcy, I'm not going to pay my mortgage. Same thing happened in Ireland, a few other countries. So a few million bad mortgages then are amplified through credit default swaps and everything else. So that now you have an economic system that's not resilient to that perturbation, propagates through the global economy. You wind up with a 5% loss in global GDP. And so climate change is going to manifest itself regionally. Climate change damage, right? There's going to be floods places, there's going to be droughts places, there's going to be heat-stressed crops places. And so this question of to what extent does do social systems, either economic systems, amplify this, or maybe there's political strains that result in war, and you have nuclear-armed countries and so on. And so that I think that, again, it's not just climate damage, it's climate damage and social and political systems that then can be triggered by this climate damage that could lead to some kind of global catastrophic situation. Again, so this is sort of going to where I was before. So now this is this is an older set of scenarios, but this was the temperature change from these SRES scenarios. And if you notice that this was from the previous, the third IPCC report. If you notice that even the most sort of optimistic ones of these, the temperatures never start decreasing this century. In every one of these, the global temperatures are going up. And so, what you can say is that reductions in emissions can sort of bring us from this line down to this line, or this line down to this line, and can slow the rate of warming, but it's not going to, even if we cut, again, going back to that earlier slide, even if we cut emissions to zero, we're just stabilizing temperatures. And so there's no way, other than cutting emissions to zero and sucking CO2 out of the atmosphere, is the only way to actually cause things to decrease if we were just working on the greenhouse gas side. And so, so the question is, if there is a climate emergency, where I'm meaning that is a combined emergency brought about by failure of social and political systems, as well as physical system triggers, that there's, that there's nothing you can do. In other words, if you're getting heat stressed from your crops year after year, it's likely only going to get worse. If the ice sheets, if the methane starts coming out of the permafrost, it's only going to get worse. If it's, you know, and so what do you do if one of these things happen? And really, it's really this you know, so one of the take-home things from the carbon dioxide removal stuff is that it's huge scale. It's at the scale of the energy system. It's something that takes a long time. It's not going to be cheap. You know, so the carbon dioxide things are feasible, but they're not an emergency response. There's some way of dealing with the long-term issue. In 1991, there was a huge volcano eruption, Mount Pinatubo in the Philippines. And the next year, the Earth cooled by around 0.5 degree Celsius, about 1 degree Fahrenheit. And this is because this volcano put material into the stratosphere, and this material in the stratosphere reflected sunlight back to space. So instead of the sunlight coming down and heating the Earth, it got reflected back to the sunlight. Back to space. This material fell out of the stratosphere on a time scale of about a year. And so that's why things start heating up. But the reason things didn't cool down more was because the oceans and the land surface are warm. And so even if you reduce the amount of sunlight coming in, you still have that warmth of the ocean and the atmosphere. And so, you know, if you were able to maintain that same amount of sunlight reflection permanently, it's thought that the amount of material put into the stratosphere by Mount Pinatubo would have been enough to offset all of the global warming anticipated this century. And it turns out that there wasn't that much stuff, that if you had constantly one plane flying around in the stratosphere with putting out material, you know, through one fire hose, that would be enough to maintain that much material in the stratosphere. And now there were, you know, so what happened that year? So I can say that year the Amazon River had the lowest river flow ever. Also the Ganges Brahmaputra system had the lowest river flow also. So there are definitely you know, effects on the hydrological cycle. There's also reasons to believe that here, let me just go through this one, that the oceans heat up and cool down slower than the land. And you get monsoonal type flows. When land is warmer than the ocean, then air tends to rise off the land, brings in moist air off the ocean, brings in rain, you know, that cool, moist air as it ascends, drops its rain. And so if you warm the land relative to the ocean, you tend to increase monsoonal flows and increase precipitation on land. By having a single volcano, because the ocean has more heat capacity, effective heat capacity than the ocean, the land cools off more. And so then you get less of this rising air. And so then you get less of these monsoonal flows. But that has to do with a short-term thing. And so you wouldn't necessarily expect the same effects to happen on a sustained long-term effort. But anyway, it's just, so we know Mount Pinatubo happened. Yes, there were, the Earth did cool. Yes, there were perturbations to the hydrological cycle. Yes?
And just out of curiosity, it's not my area of science, is there any controversy over the causality between the eruption and the observed reduction in temperature?
No, this is basically well established. And no, I would say, I haven't heard anybody say, no, that was just random fluctuations. I mean, there was, you know, there was, I mean, if you notice in this slide here, I mean, there was an El Nino around the same time. And so this black line was the actual observed temperature. And so then people, there's an argument, there have been arguments about, well, how much of this was due to El Nino and how much of it was due to the aerosol. And so this paper was, one of the things it was doing was saying, well, if there hadn't been an El Nino, it would have been this dashed line. So, I mean, this is kind of, so everybody agrees that on the sort of order of magnitude of temperature reduction, and people are arguing in the tens of percents which to attribute it to, but the basic physics nobody disagrees with. So, what are the, so there's a whole range of things that have been proposed, and this is a cartoon to go through those. And I think I have more, but one idea is to put giant satellites in space, and one idea is to put it in space between the Earth and the Sun. Other people have the idea of orbits, but it's and then another idea is to put a layer, do as volcanoes do, and put a layer of material in the stratosphere. Another idea is to whiten or brighten clouds over the ocean. Another idea is to sort of whiten the surface of the ocean. Or plant lighter colored crops, or put on white roofs. And Secretary Chu for a while was promoting this approach. And so let me go through each of these. Yeah, so one idea, and this was put forward by one of Edward Teller's colleagues, this idea of putting satellites at there's L1 point between the Earth and the Sun. And there's basically a point that's where the apparent centrifugal forces and the real gravitational forces of the Earth and the Sun are all balanced, such that it's like a ball on the top of a hill, that with very little energy you can just keep it in place and it'll sit between the Earth and the Sun. And the main problem with this is if we just wanted to keep the Earth the same temperature, and we continued emitting greenhouse gases at the rate we're emitting, you would need to build this satellite just to compensate, not for past heating, but just for the current rate of heating. You'd have to build a square kilometer of satellite every half hour and get it out into space. And just that if you were to do something at that level of effort, again, it's like, wouldn't it be easier just to build the right kind of energy system rather than trying to build this thing, But if you get into, to me, this sort of idea of satellites in space to prevent global warming is kind of science fiction stuff. If we have a sweltering planet 500 years from now, maybe they'll do that. But it's not. The other thing is this: if the idea of these things is supposed to be emergency response, and you have to build, tens of thousands of square kilometers of satellites millions of miles away, or a million miles away, that's not an emergency response. So this idea of stratospheric aerosols, this idea of emulating what volcanoes do, is, seems to me to be the dominant approach. And people have gone and, now, what the volcano did was put sulfur into the stratosphere and oxidized to form sulfate particles. And so a lot of the attention has focused on sulfate particles, but really any particles of approximately this right size, which is sort of a tenths of a micron scale, would do the job. And people have sort of come up with, and again, Edward Teller and his colleagues, even as in the late 1980s, designed, at least on paper, all kinds of exotic particles with different properties that would reflect different parts of the spectrum or who knows what. Yeah, so let me just actually tell a little story about Edward Teller on this one. That Edward Teller, when after the atomic bomb was dropped on Nagasaki and Hiroshima, Edward Teller thought, oh, now nuclear war is thinkable, and people, we're in an age of nuclear war, and he didn't trust social systems to prevent nuclear war. So he said, what's the technological solution? And he said, okay, let's make a bomb so bad, the super, that people will be afraid to use it. And so he created Lawrence Livermore Lab, which is about an hour away from here, to develop the hydrogen bomb. And he said, we'll make a bomb that's so terrible that people will be afraid to engage in war. And Oppenheimer was against this and all that. And so, but anyway, Teller got Livermore, the hydrogen bomb was developed. And for a few decades, nobody dropped any nuclear bombs, and Edward Teller said, "See, I'm justified. I was right." And then by the early 1980s, there's all these multiple independently targeted reentry vehicles and all that started making the idea of first strike thinkable. And so Teller was saying, okay, the nuclear war is once again thinkable. I don't trust social systems, the START Treaty and so on, to solve this problem. Let's think of a technological solution that will make first strike impossible. So he got this idea of the Star Wars missile defense system. He walked into Ronald Reagan's office and just basically convinced Reagan to go with it. And boom, there was the Star Wars missile defense system. And so, so Teller never, he was an optimist about technology and a pessimist about social systems. So he thought, look, we can never get social systems to solve problems, but we can invent technologies that solve problems. And so by the late 1980s, he started thinking about the climate problem, and he said, look, we're never going to get it together to reduce emissions, but maybe we can come up with some technical solution. And so they wrote a series of papers, starting I think in 1989, on space-based and stratospheric-based aerosol designs, and basically saying, look, let's find a technological way out of this problem. Anyway, the stratospheric aerosols one just seems feasible. I mean, there's no technological roadblocks. There's still some questions about aggregation of particles in the stratosphere and what might it do to the ozone layer and so on. But I think the fact that the Earth has cooled multiple times due to volcanoes and that nothing catastrophic happened at a global scale as a result of those, and the expectation is that a sustained layer would probably have fewer, yes?
Ken, has anybody modeled the phase out of high sulfur bunker C fuel and shipping over the next 10 years?
Yeah, I don't know model, but back of envelope calculation. So one of the, let's actually go to the next one, is this idea of cloud albedo changing, which is related to this. So one idea is to, so if you look out and you see rain cloud, a cloud that's about to rain is gray. And the reason it's gray is because the cloud has big droplets in it. And the same thing, if you get like big rock salt and the particles are kind of gray, but if you crush that salt down to fine particles, it's like a white powder. And with clouds, it's the same thing. If you have big droplets, the cloud looks gray. A cloud with lots of little droplets is whiter. And so in the same way that parts of the ocean don't have enough iron, and it's often the same reason because there's no dust falling on it with iron in it, the parts of the ocean, the sky is so clear that there's not enough nuclei around to make enough cloud droplets to allow the cloud droplets to be small. So cloud droplets can't just, because of thermodynamics, can't just form out of thin air, so to speak, that they need to, the cloud droplets need to nucleate on a little piece of dust or something. And so one idea is to spray seawater in the air and find sea salt particles and whiten clouds. And the other thing, if you look from satellites from space, you see ship tracks because there's sulfur particles coming out of ship smokestacks, and that leaves kind of contrails across the ocean. And I'm trying to remember which was the International Maritime Organization, I forget which treaty it was, but they're trying to get rid of these high sulfur fuels. And my recollection was just that one rule was a couple of tenths of watts per meter squared globally, I think. I forget the exact number, but it's sort of not, so basically by losing these ship contrails, now you have dark ocean or darker clouds.
The other part of the question is the phase out of once through cooling water forcing cooling towers instead. Is there a noticeable impact there as well on the cloud front?
Okay, now the cooling towers, we did a study of looking at what does evaporating water do on average. Now this will vary locally a lot. So water vapor is a really complex thing because there's a water vapor greenhouse effect. But water vapor can also make clouds, and clouds are white, and it reflects sunlight back to space. But also if clouds are high enough, tops can be cold, and they can actually sort of act as a blanket and keep the long-wave radiation in. So, this question of does evaporating water, what does that do to the climate system? And we did a study published a year or two ago that said on global average, for each watt you put into evaporating water, if you release that CO2 low in the atmosphere, the dominant effect is forming low clouds. And you increase the reflectivity of these low clouds. And so for each watt that goes into evaporating water from, say, a cooling tower, that probably a half a watt to 3/4 of a watt gets reflected to space. And so actually, if you're just worried about the climate system, there's an additional cooling effect in most places just by releasing the steam into the atmosphere. This could vary a lot locally. If you release the steam, say upstream from a desert, you might not form clouds there, and maybe the water vapor greenhouse effect will dominate there. Yeah?
Didn't you just say that that's an energy loser? It takes a lot to reflect half a watt?
Yeah, well, the thing is this, if you're, right, so if you could capture that energy and use it, then you're better off capturing the energy. But often the reason why it's in a cooling tower is because it's already, you've already gained what Carnot lets you gain or whatever, and you have, so the answer is yes, if you could capture that energy, it would be better to, and you could somehow have that energy substitute for fossil fuels, you're better off doing that. But if you have steam, say low temperature steam that it's coming out the back end of your power plant, and you have a choice of just releasing that steam to the atmosphere or condensing it. Yeah?
I think this a little bit differently in terms of it takes you energy to evaporate the water, but then you're talking about a power level that you are reflecting. So one's for a duration of time, the other one's for a unit of power to get it started.
No, I think the units are right, because I'm saying for each watt of energy that is sort of, let's say as that water condenses, for each watt of water that, the latent heat represented by that steam, that being in the atmosphere would reflect like a half or 3/4 of a watt to the atmosphere. But actually this, we wrote this paper, but nobody's brought this up in the context of power plant cooling towers, if you wanted to.
Well, EPA has the phase out for the U.S. on these once-through cooling is in place now. So these big steam power plants have to remove that low-level heat to condense the steam under vacuum. And the issue is a lot of them are once-through cooling now, where you have a diluted temperature, usually ultimately into the ocean. The other is a cooling tower, which clearly puts more of that vapor into the atmosphere. And if there's a reasonable effect, there's a lot of power plants around the world that have the same issue. However, it does increase the cost and reduce the efficiency of the power plant, maybe 2%.
What reduces to condense?
To recycle cooling power as opposed to once-through cooling.
Well, this is interesting because, I would just say, if your only goal were to make the planet cooler, just releasing the steam to the atmosphere. It's kind of counterintuitive. People might think, oh, well, burying that heat in the ocean or something might be better. But my intuition of our simulations and how the climate system works, that really if you want to cool the Earth, the best thing is just to release the steam to the atmosphere. It's an interesting one. Yeah, so this is these edges of geoengineering, right? So do you count, a power plant releasing steam to the atmosphere as geoengineering? If your intent is to alter climate, maybe it is. I don't know. Okay, so there's this other idea of putting plastic over deserts or whitening roofs, and my joke on whitening roofs is, you convince the people in Montepulciano that they should start looking like Santorini. And I think this one, first of all, you can just do the calculation. There's not enough area of built surfaces, so this could be helpful for the urban heat island effect, but it's in terms of global cooling. So I think. And then with that, there's also controversy of green roofs versus white roofs. This gets into another again, a lot of interaction between the climate system and the social dimensions, that often if you plant a tree, even though there's some carbon storage, so there's a cooling effect, and there's this increased evaporation usually, which is usually also a cooling effect. But also, often the forest is darker than, say, the pavement. Or, if you plant a tree in a paved area, that's darker than the pavement, and you can actually absorb more sunlight and have a net heating effect. But still, if you're somebody living in an urban center, being in the shade under a tree can be a lot nicer than setting up your folding chair on the middle of a hot sidewalk. And so that, so that even though the air temperature might be 1/10 of a degree warmer, you're in the shade and you feel better. And so this question of, is it better to have a white roof or a green roof? And, do we want to green our cities or whiten our cities is a complicated issue. And this was sort of pushed, anyway, the folks at Berkeley, Lawrence Berkeley, were pushing this, and Secretary Chu pushed this idea for a while, although I think the people at Berkeley discovered that it was better to be ignored than to be touted, because if you're touted one year and people slap you down, your budgets get cut the next year. My understanding is that before Secretary Chu said anything about this, it was, I should be careful, this is being videotaped here, so I'll just go on to the next topic. Okay, basically, okay, let's just, I was just saying, okay, I'm not going to go there. So so there was this study that just got published. This was sort of the white paper was referred to in The Economist, but it was just published in, I think, Environmental Research Letters as a peer-reviewed study. And this was the cause of putting 1 million tons of sulfuric acid into the stratosphere. And they got numbers that were, depending on the altitude, but, were, under $1 billion a year for their, what they thought would be the best design. And, you have to put in several times this, but more or less, the idea was that the direct cost of putting this much material into the stratosphere might be a couple of $2 billion a year, which means that, really though, you'd want a satellite system to be observing Earth's radiation balance and monitoring, and there's liability issues if somebody, if a typhoon the next year was generated where there was never been a typhoon before and they get hit by this typhoon, are they going to sue you saying that you caused this? And this actually happened with in the 60s, there was a program to try to control or at least influence the behavior of hurricanes. And this was a U.S. research program. And there was one hurricane that their intervention probably didn't do anything to the real trajectory of the hurricane, but it was, I'm trying to remember, I forget what city it was, but some city in South Carolina, it was like heading towards a city, and so the idea is that if you are able to influence a hurricane and it was heading for, say, New Orleans, and you manage to move it over so it hits 100 kilometers away, and so yes, you saved 2,000 people in New Orleans, but now you've killed some people 100 kilometers away, and those people are going to say, well, look, you've damaged us, and so these kind of liability issues, I think, make it so, first of all, only governments can really do these kind of things, yeah?
Does this include the cost of acid rain damage?
Yeah, so the acid rain damage is the amount of acids we're talking about for doing this is around 2 or 3% of what's currently coming out of power plants. And so, you could say, well, if I, so, I mean, you could sort of deploy this, and if you really cleaned up all your power plants, it'd be at 2 or 3% of our current acid rain. And so I think it's one of these things, all these things are, nothing's perfect and everything is a balance. And, I think if we were in a real climate crisis and people were starving and famines and all that, then the acid rain one might, at that 2 or 3% level, would be not the hugest concern. The other thing is that there's no reason you have to use sulfur. There are basically any small particle of the right size could do the job. So anyway, I'm really close to the end of this, and I didn't get through much of it at all. So, but anyway, just to show that, climate models say that it works pretty well, and if you put more at the poles, it would probably work a little better. In a typical, even a uniform distribution of aerosols offsets, say, 90% on average of the seasonal and regional climate change, and maybe for the precipitation reduces the amount of precipitation change by maybe 70% or so. And so this is, I'll just run on because I'm in my last minutes. But I think this is the basic upshot, is that the climate change can offset most climate change in most places most of the time. Let's just go to this one. So this thick lines are over land. So this is like just for 2 times CO2, and this blue line is with uniform aerosol distribution. And then the same thing, this is the change in precipitation, is this red line over land. This blue line is with a uniform. And so, yes, there are places where precipitation is reduced, but the overall amounts of change are dramatically less than with just climate, just CO2 in itself. And so, so basically they can offset most climate change in most places most of the time. That's not to say that some people aren't going to be damaged some of the time. The rate at which this thing, here we have simulations here where you sort of turn it on at different times, and more or less you get, half the cooling or so within a decade or so after a change in radiative forcing. So the effect is pretty dramatic, and that's seen with after Mount Pinatubo. I'm not going to go through all this. So let me just run through this. So we did a study looking at crop yields, and basically what we found was, at least in the climate models, that crop yields increase under these scenarios. That the first one idea might be that because you were taking away some sunlight, that's going to harm crops. And it turns out that the biggest effect is really the heat stress effect, and that the increased, by cooling things down, you reduce the respiration rates of the plants, and so you allow them to accumulate biomass faster. And that effect is bigger than the reduction in sunlight. More or less, the photosynthesis scales with the reduction in sunlight. So you're getting say for blocking 4% of sunlight or 2% of sunlight, you cut photosynthesis down by 4 or 2%, but then you're cutting down the respiration by much more. And so at least in these models, which are the same model, again, it's simplistic, but same sorts of approaches used to predict the effects of climate change, get substantial increases in crop productivity. So more or less what's happening in this model is that you're canceling out most of the climate change, and so the crop yields would go closer to what they were pre-industrially, but since CO2 allows crops to get better, utilize water more efficiently, you get the benefits of CO2 fertilization without the negative parts of the climate change. So at least in this, and this was done in 2 different climate models, and the result was basically the same. So so I guess I'll just wind up saying, anytime you interfere in complex systems, things happen that you don't anticipate. And the case example is the introduction of cane toads in Florida, which I forget was a slug or snail that was eating their sugar cane, and they said, oh, let's introduce a natural pest to our crop, and then now the cane toads have taken over and are running rampant, and they have poisonous skin, and so dogs eat them and die, and all this kind of stuff. On the other hand, the Australians did introduce dung beetles because they had a problem with all kinds of flies growing on cow patties, and they didn't have any native things that would eat the cow dung. And they looked they looked at species of beetles that would live in pastures that wouldn't enter the forest and so on. And it's thought that the introduction of dung beetles has been a successful way of controlling insects on cow patties. And so, but anyway, anytime, I think you just have to assume that anytime you interfere in a complex system, it's more complex in our models, that things are going to happen, whether it's on the physical climate side or the social and political side that you don't anticipate. And there's many sources of risk. I didn't go into this so much, but there's this who's going to set the knob of how much we're going to do, and if one country doesn't want to do it, one country does, there's political problems. Risk of complacency, that people say, oh, there's a technological fix so we don't have to reduce emissions. Chemical risk, maybe the ozone layer will get damaged. Ecological risk, I didn't mention this, but a lot of the sunlight no longer comes down directly but gets diffused, and so this can affect the canopy structure in ecosystems, and what if this thing's poorly managed and it fails, et cetera, et cetera, et cetera. And so, I think we're in a case where we sort of have to balance, increased risks with potential for risk reduction. And right now, we're in this state of not really having that much knowledge about these systems. So I will close there and just go back to this last thing here. Okay. I think I could release you to your lunch, but if anybody wants to ask any last questions, I could, yeah.
So if you were an intelligent species visiting our planet, maybe a couple years or maybe right now, what advice would you give us based on what you presented today about, do we fix things before we enter this regime, or do we think about this?
Well, if I were like king of the world, I would say let's stop making devices that use the atmosphere as a waste dump. I would start there. I think that one of the things is this, that if the lowest risk, if I said that a full-scale implementation of this, of Mount Pinatubo level, would counteract all the warming this century, I think a rational approach, and if you see the trajectory we're on now, it's up and up and up. I think a rational approach would be to implement at a 1% level next year, see what happens. Just offset the increase. Then you put it 2% the next year, 3%. And then if something bad starts happening, taper it out. But the problem with that is, so then you're sort of tiptoeing into it. If something bad happens, you try to tiptoe your way back out. I think from an environmental perspective, that's the least risk. Politically, you'll never get consensus, I think, outside of a crisis. And so from the least sort of politically risky thing is don't do anything, wait for something catastrophic to happen, and then turn it on full bore all at once. Which is the most, and so I think we're in a thing where the actual risk, the path that has the most risk-averse path, I think, is the least politically viable. And I think the riskiest path is the path that's most politically viable.
This is something about our social and political system.
Yeah, that's why I say all these things, the more, I think the more I study the physical climate system, the more I'm convinced that the main issues are really in social and political systems.
If we got 0.2 degrees or 0.2 watts per square meter from high sulfur fuels, why not go back to a tropospheric approach, and what are the limitations of doing that, let's say, just over the oceans?
Well, this is like Mike McCracken has been pushing this today over the Arctic. It's thought that some of the Arctic warming of the last decades is due to Europe cleaning up its sulfur, and North America to a lesser extent clearing up its sulfur emissions, and that a lot of this relatively sudden Arctic warming is a consequence of cleaning up our power plants, and that if China, I forget what China's sulfur emissions are, but it's somewhere close to a watt per square meter of forcing, maybe half a watt, something like this, and that, so, I think especially, I think these regional approaches might be possible, but the real difference is that in the troposphere, particles last around 5 days, whereas in the stratosphere, they last around a year. And so, what's the ratio of 5 to 370, whatever. So you have to put sort of like 70 times as much stuff if you're going to put it in the troposphere, but there's no reason why, in principle, that couldn't work. Although then you have 70 times bigger acid rain problem and all of this.
Can you argue that the cost is 70 times less if you're not elevating it?
I don't think it's 70 times less, but it would be less. Another sort of thing of this is you can imagine China, not that they're motivated to do this, but if they said, well, for each power plant that we clean up, if we put 2 or 3% of that in the stratosphere, or 1% of that for each power plant you clean up, if you put 1 or 2% of that sulfur in the stratosphere, we would have cut our sulfur emissions by 98 or 99%, but not lose the climate effects, the cooling effect of that sulfate, and so I think this thing of slippery slope. I didn't get into this whole political thing, but if China did that, not that I don't think they're motivated to do it, so I don't think they would, but I don't think anybody would really want to start a war with China over something like that. So I think this case where somebody really turns on full blast something and tries to change the whole world's climate, I don't think it's a lone actor can get away with that. But if some powerful country were to do, if Russia started doing some little thing at a 1% level, I mean, they might get some diplomatic, feedback from that. But I don't think anybody's going to attack Russia because of that. Kim?
There are some soft geoengineering approaches as well that are being proposed to brighten water or to brighten snow and ice.
Yeah, I didn't go into this. You're working on brightening snow and ice, but there's like other ideas to like make a foam or micro bubbles in the ocean and try to cool whiten water. In fact, in 1965, there was the President's Science Advisory Committee, or the PCAS report, but it was the first time a president was told about the global warming problem. And this was reported to President Johnson, and the proposal was to float white things on the surface of the ocean to reflect sunlight to space. And so as a policy response to global warming at the presidential level, geoengineering was introduced prior to the concept of emissions reduction. So the first thing that was proposed was geoengineering, and it was only later that people thought about emissions reduction. So I better let you get to lunch, otherwise you'll be hungry. So thank you again.